Okay, picture this. You've got this massive bin, right? Just full of Legos, every single piece you own, all jumbled together.
Chaos.
Total chaos. It's that exact feeling we're tackling today, but for computer data.
Right.
We're diving deep into something called database normalization, basically turning that digital junk drawer into something,
Hmm?
well, organized,
Yeah.
optimized.
Yeah, and that Lego analogy, it's actually a surprisingly spot on for what we call unnormalized data.
Really? How so?
Well, when you just cram information together like that, you run into immediate problems. Finding one specific thing suddenly really hard.
Okay.
You've got bits of data sort of weirdly stuck together that don't really belong. And maybe worst of all, you repeat the same information over and over again.
Okay. Like having the same type of red bricks scattered everywhere instead of grouped.
Exactly. And in a database, that doesn't just mean it's messy. It means it's slow, confusing, hard to update reliably. It actually starts to undermine the trustworthiness of the data itself.
So it's not just messy, it's actually problematic. We need a system, a way to tidy up. Where do we even start with this digital Lego box?
Well, the very first step, the foundation really, is getting to what's called first normal form, or 1NF for short.
1NF. Okay. What does that involve?
Technically speaking, it means making sure every column, every sort of cell in your data table holds only one single piece of information. Atomic, we call it.
Atomic, like indivisible.
Precisely. So if you have, say, a column for phone numbers, you wouldn't put 555-1234, comma, 555-5678 all in one cell.
Oh,
Each number gets its own row or maybe its own dedicated phone number entry linked to the person, one value per spot.
gotcha. So it's like finally getting one of those Lego organizer trays, with all the little compartments.
Hmm.
And you put one specific type of piece, like a single blue 2x4 brick, in each little compartment. No clumping allowed.
That's a perfect way to think about it. One piece per spot, you eliminate those clumps, those multi-valued fields.
And what does that immediately fix? Just doing that one thing.
Oh, it's huge. Suddenly, searching becomes way easier. Imagine trying to find everyone with the phone number 5555678 if it's buried inside a comma-separated list in some cells.
Nightmare.
Total nightmare for the database to search efficiently. 1NF makes each piece of data distinct and addressable. It's foundational for just basic data handling and accuracy.
Okay, so we've done the first sort. Everything's atomic, one piece per spot.
Yeah.
But like even in my organizer tray, I might have mini figureheads next to spaceship wings. They're separate, but not really grouped logically yet, right?
Exactly. Separation isn't the whole story. That leads us to the next step. Second normal form, 2NF.
All right, 2NF. What's the rule here?
So 2NF really comes into play when you have what's called a composite primary key.
Composite meaning multiple parts.
Yeah, where you need two or more columns together to uniquely identify a row. Like maybe order ID and product ID together define one line item in an order.
Okay, makes sense.
The rule for 2NF is every other piece of information in that row, all the non-key details, must depend on the entire composite key, not just part of it.
Okay. Let's go back to Legos. Say I have a big box labeled Star Wars ships and their pilots. Maybe the key is the combination of ship name and pilot name.
Right, that could be a composite key.
So inside I might have ship color, which depends on the ship, and pilot species, which depends on the pilot. But what if I also put pilot blaster type in there? The blaster type only really depends on the pilot, not the specific ship they're flying right now.
Exactly, that's it. The pilot blaster type only depends on part of your composite key, pilot name. That's called a partial dependency, and it violates 2NF.
Ah. So that detail doesn't belong in the ships and pilots box. It belongs somewhere else, maybe a pilot's box.
Precisely, you'd split it out. So in a database, if you had order ID and product ID as the key, but you also stored product name in that same table.
Wait, the product name only depends on the product ID, right? Not the specific order it's in?
You got it. That's a partial dependency. So product name would get repeated for every single order that includes that product. Huge waste of space and potential for inconsistency if the name changes.
So 2NF forces you to put things like product name in their own products table, identified just by product ID.
Exactly. It's about making sure everything in the table is describing the whole unique identifier, not just a piece of it. Cleans up a lot of redundancy.
Okay, we've tackled the obvious clumps with 1NF, and now with 2NF, we've made sure details are tied to the whole main topic or key. But you mentioned things can get subtle. Is there another layer?
There is. And this one can be a bit trickier to spot sometimes. It's called third normal form, or 3NF.
3NF. All right. What kind of sneaky disorganization are we hunting down now?
We're looking for something called transitive dependencies.
Granted, like indirect.
Yeah, that's a good way to put it. It's when you have a non-key attribute, just a regular detail column that depends on another non-key attribute, instead of depending directly on the table's main identifier, the primary key. It's like a chain reaction.
Okay, let's try the Legos again.
Yeah.
Maybe I have a Star Wars ships box, and the main key is just the ship name, like Millennium Falcon. Inside, I have pilot name, say, Han Solo. That depends directly on the ship, fine. But what if I also put pilot home planet Corellia in that same Star Wars ships box?
Ah, I see where you're going.
The pilot home planet, Corellia, doesn't really describe the Millennium Falcon itself, does it? It describes Han Solo.
Right.
So the pilot home planet depends on the pilot name, which then depends on the ship name. It's indirect, transitive.
That's a perfect example of a transitive dependency. The home planet depends on the pilot, which depends on the ship's primary key. It shouldn't be in the ship's table.
So 3NF says I should take pilot name and pilot home planet and put them in a separate pilots table linked by the pilot's name or ID.
Exactly right. Or think about a customers table. You have customer ID as the key, customer name, maybe city, and zip code.
Okay.
Now, in many places, the specific zip code always determines the city, right? Like that 90210 is always Beverly Hills.
Yeah, usually.
So in that table, city doesn't really depend directly on the customer ID. It depends on the zip code, which then depends on the customer ID.
Ah, another transitive dependency.
Yep. So 3NF would say move city and zip code to their own zip codes table, with zip code as the key, and just keep the zip code in the customers table to link them.
Why is that better? Seems like extra tables.
It prevents problems. What if the city name associated with the zip code changes slightly? Or you have two customers with the same zip code, but you accidentally type different cities. With the separate table, you update the city for that zip code once in one place, and it's consistent everywhere.
Ah, okay. Consistency. That makes sense. Fewer chances to mess things up.
Exactly. 3NF is about ensuring every non-key attribute provides a fact directly about the key, the whole key, and nothing but the key, so help me COD. Well, maybe not the last part.
Huh. Okay, so we've gone through 1NF, 2NF, 3NF. It sounds like a lot of careful sorting and splitting. Why go through all this trouble? What's the big win at the end of the day?
The payoff is it's really significant, especially as data grows. The most obvious win is drastically reducing data redundancy, less repeated data.
Which means,
Less storage space needed, faster backups, less data to push around. But maybe more importantly, it massively cuts down on what we call anomalies, weird issues with updating, inserting, or deleting data.
like the inconsistent city names example.
Exactly. That's an update anomaly. Or imagine trying to add a new product that hasn't been ordered yet. If product name is in the order items table, violating 2NF, you can't add the product info until there's an order. That's an insertion anomaly. Normalization helps prevent all that.
So it's not just about being neat, it's about making the data trustworthy and easier to manage correctly. If I change a customer's address, I change it in one spot, not potentially 50.
Precisely. Think about a big online store. Millions of products, customers, orders. Normalization means their database queries can run in milliseconds instead of minutes. That affects everything: website speed, report generation, customer satisfaction. It saves real money on infrastructure, too.
Okay, so it makes databases faster, more reliable, easier to scale and maintain. It's the foundation for systems that actually work properly.
Absolutely, it's foundational. Now, are there times developers might choose to slightly denormalize for very specific performance reasons? Yes, sometimes, but that's an advanced topic, and it's always a conscious trade-off. You absolutely need to understand normalization first. You have to know the rules before you can effectively bend them.
So when we boil it all down, database normalization, it really is like intelligently organizing that chaotic Lego box, making sure every single piece has a logical place to live.
It is. It's about smart, deliberate organization. But, maybe take it one step further. Think about what that organization enables.
Go on.
Well, these principles, they're not just about making a database tidy or fast. When information is structured well, when it's clean and reliable, it becomes a foundation you can truly build on. It impacts the accuracy of your analysis, the confidence you have in making decisions based on that data. It affects the long-term usefulness of the information. So maybe the deeper question isn't just how do we organize data, but how much more powerful do our insights and innovations become when they stem from data we fundamentally know we can trust? What future discoveries rely on getting this foundation right now?